Okay, strap yourselves in, because today we're going deep into the world of work, energy, and power.
The invisible forces behind, well,
Everything.
pretty much.
That's right, we're talking physics.
And you want to understand these concepts better, right?
Oh, absolutely.
But let me tell you, sometimes the way us physicists define these terms,
Ooh, here we go.
it's a little different than how we use them every day.
I bet. Like walking my dog, that's work for me, but
Right.
I don't know if physics would agree.
You're on the right track.
Okay.
That's exactly what we're going to explore today.
Awesome.
Uncover some pretty mind-blowing stuff.
Mm-hmm.
For example, did you know you could be exhausted without actually doing any work?
Really?
Physics terms, of course.
Oh, okay.
Or that a tiny raindrop falling
Yeah.
involves this fascinating energy trade-off.
Okay, now you've got me hooked.
All right.
So let's start with work.
Okay.
I am ready to have my mind blown.
All right, so get this. In physics, work only happens when a force moves something over a distance.
Okay.
So think about pushing a heavy box across the floor.
Yeah, like moving.
You're putting in the effort. That box is moving.
So that's work.
Classic work.
Okay, so far so good.
Right.
But it's about to get more complicated, isn't it?
Well, here's where it gets interesting.
Okay.
Only the part of the force that's pushing in the direction of the movement counts as work.
What?
So if you're carrying that heavy box,
Yeah.
but you're walking in a straight line,
Okay.
you might not be doing as much work as you think.
Hold on. How can carrying something heavy not be work? My arms would be killing me.
Think about it this way.
Okay.
When you're carrying that box, you're mainly using force to hold it up, right?
Yeah, to keep it from
Exactly. But the movement is horizontal.
Okay.
So most of your effort
Right.
isn't going into moving the box forward.
Uh-huh.
It's going into fighting gravity.
So most of my energy is just me losing a battle to gravity.
Pretty much. And here is the real mind bender.
Okay.
Holding a weight still.
Yeah.
Even if it feels super tired.
Yeah, like a plank or something.
Exactly. Technically means you are doing zero work in physics terms.
No way.
No distance moved equals no work done.
Wow, that's going to mess with me at the gym.
Right.
What about, okay, so in real life, sometimes like the force you're using changes.
Oh, of course.
You know, as you go. So like, imagine someone pushing a big, heavy trunk and they're getting more and more tired.
Oh, yeah.
How does that work?
That's a great point, and it brings up a concept called variable force.
Ooh, fancy.
So think of that person pushing the trunk, right?
Mm-hmm.
At the beginning,
Yeah.
they might be pushing with a lot of force.
Oh.
But as they get tired, that force decreases to figure out the total work done.
Right.
You have to consider how the force changes over each tiny little bit of distance and add it all up.
So even in like a messy real-world situation, physics has a way to
absolutely
calculate the work done.
Physics always has an answer.
Interest. Okay, let's move on to kinetic energy.
All right.
Now that sounds exciting.
Kinetic energy is pure motion energy.
Okay.
Anything that's moving has it.
Oh, okay.
A speeding bullet, a rushing river.
Yeah.
Even you walking your dog.
I love that even my lazy dog walk involves physics.
It all comes back to physics.
But how do you actually measure this energy of motion?
It all boils down to this, honestly, quite simple formula.
Okay.
Kinetic energy equals 1/2 times the mass of the object times its velocity squared.
Okay.
It's written as KE equals 1/2 mel of V squared.
Okay.
And that velocity squared part is super important.
Okay.
It means that even small changes in speed can mean big changes in kinetic energy.
Wait, so if I double my speed on my bike, my kinetic energy doesn't just double. It
quadruples.
Quadruples.
Yeah.
That's wild.
It is pretty wild. To illustrate this a little further, imagine a bullet fired from a gun. As it tears through a piece of wood, it slows down significantly.
Okay.
Let's say by like 68%.
Okay, a lot.
A lot, you might think.
It would still have a lot of energy.
Right, exactly.
Yeah.
But the truth is, because velocity is squared in the formula, the kinetic energy actually plummets.
Dramatically.
Dramatically.
So a seemingly small change in speed can have this massive impact on kinetic energy.
Absolutely.
My mind is blown.
It's pretty wild.
Okay.
Yeah.
So we've got work, we've got kinetic energy. They both relate to like movement and stuff.
Yes.
But how are they actually connected?
That's where the work energy theorem comes in.
Okay.
And this is honestly one of the most fundamental ideas in physics.
Ooh, okay.
This theorem says that the net work done on an object directly equals the change in its kinetic energy.
Oh.
It's like a cosmic equation. That balances the energy books.
So like every time I'm pedaling harder on my bike and I speed up, I'm literally converting the work from my legs into motion energy.
Exactly.
Oh.
And it works the other way, too. If something slows down, like a car braking, the change in kinetic energy is equal to the work done by the brakes.
So it's this constant give and take.
Yeah, it's a beautiful balance.
Between work and kinetic energy.
Absolutely.
But let's not forget about
that
other energy, the one that's just waiting to be unleashed.
Yes.
Potential energy.
Potential energy, yeah.
Yeah.
It's the energy that's stored within an object.
Okay.
Because of its position or configuration.
Okay.
So think of a roller coaster at the very top of a hill.
Oh, yeah.
It's full of potential energy just waiting to be converted into motion.
So potential energy is like energy on hold.
Yeah, pretty much.
Okay.
It's there. It hasn't sprung into action yet.
A stretched rubber band.
Perfect example. The more you stretch it, the more potential energy it stores.
But what about something like a book on a shelf?
Oh, that's a good one.
Where's the potential energy there?
Well, think about
It's not going to like launch off the shelf.
Right, but think about what would happen if you nudged it.
It would fall.
It would fall.
Okay.
Right, and that's because it has potential energy due to its position above the ground.
Oh, okay.
The higher an object is, the more gravitational potential energy it has.
So if I lift a weight higher,
yeah,
I'm giving it more potential energy.
Exactly.
No wonder weightlifting is so tiring.
Yeah, right.
It's all that potential energy.
Exactly.
Okay, and then
there's a neat formula.
Oh, there's always a formula
to express this too.
Okay.
Gravitational potential energy equals the object's mass times the acceleration due to gravity times its height above the ground.
Okay, and we can't forget about...
Oh, and we can't forget about springs.
Springs.
Yeah.
Like a tightly wound spring in a toy.
Exactly.
The bouncy potential of a trampoline.
Yeah.
Okay.
The more you compress or stretch a spring, the more potential energy you're storing up.
Right.
And the moment you release it, that potential energy transforms into kinetic energy.
Okay. Things start moving.
Things start moving.
I'm starting to grasp this potential energy thing.
Yeah.
It's like, it's all about waiting.
Yeah, it's the waiting game.
Energy is stored, ready to be unleashed.
It is.
But how does this all tie into the grand scheme of energy conservation?
Ooh, this is where it gets really good.
Things are about to get cosmic, huh?
They are. You're absolutely right.
Okay.
This brings us to one of the most fundamental principles in physics.
Uh-oh, here we go.
It is a big one.
Okay.
The conservation of mechanical energy.
Okay.
All right, so...
That sounds serious.
It is, but it's also incredibly elegant.
Okay.
So, this principle states that in a system where the only forces at play are conservative forces, like gravity or those ideal springs we talked about, the total mechanical energy.
Right.
That is, the sum of kinetic and potential energy always stays the same.
Wait, so no matter how an object moves or how its energy shifts between kinetic and potential, the total amount never changes.
The total amount never changes.
That's amazing.
It is. It's a beautiful thing.
It's like...
like a perfect...
Yeah, like potential to kinetic and back again.
Exactly.
Like a pendulum swinging.
That is a fantastic analogy.
Oh, good.
Imagine a ball on a string swinging freely.
Okay.
At its highest point, it comes to a stop.
Right.
Briefly.
Yeah.
At that moment, all its energy is potential energy.
Okay.
As it swings downward, that potential energy gets converted into kinetic energy.
All right.
And then as it swings back up the other side, the process reverses. Throughout the entire swing, the total energy remains the same.
So it's just constantly shifting.
Constantly shifting.
Between those two.
Between the two.
Okay.
It's beautiful.
This is mind-blowing.
It is.
It's like the universe has this built-in accounting system.
Yes.
That's always making sure that...
Making sure everything is balanced.
The energy books are balanced.
Absolutely.
But what about those situations where energy seems to, like...
Oh, yeah.
Disappear?
Like disappear.
Like when friction slows things down.
That is a great question.
Yeah.
And it leads us to our next fascinating topic.
Ooh, I love fascinating topics.
I know, right? Power.
Power.
Yes.
I thought we were talking about energy.
We are, but power is all about how quickly work is done.
Okay, so it's like the speed of work.
Yeah, you could think about it that way.
Like, so lifting a heavy weight slowly might take the same amount of work as lifting it quickly, but the fast lift.
The fast lift requires more power.
Okay.
You had it. Power is essentially the rate at which energy is transferred or transformed.
So a powerful engine can do the same work as a weaker engine, but it can just do it faster.
Exactly.
Oh.
We see examples of power everywhere in our daily lives.
Okay.
Think about an elevator.
Okay.
To move upwards at a constant speed, that motor has to deliver enough power to overcome both the force of gravity pulling the elevator down and any friction working against its motion. The faster the elevator needs to go, the more power that motor needs to deliver.
That makes sense, and I bet we see, like, the unit of power, the watt.
Oh, yeah.
All the time.
All the time.
Yeah.
Every time you look at a light bulb, that 60 watts tells you how much power that bulb is using.
Yeah, that's so cool.
It's incredible.
That something as fundamental as power is something we interact with.
Every day.
Every day.
Pretty much.
This has been incredible so far.
Good.
But before we wrap things up, there's one more topic that I'm dying to explore.
Okay.
Collision.
Collisions, yes.
Yeah.
Collisions are fantastic. They're a fantastic way to see the principles of energy and momentum in action. They happen everywhere. From billiard balls clacking on a pool table to atoms bumping into each other.
Whoa.
In the air we breathe.
It's like a microscopic dance.
It is.
Of energy and motion.
Exactly.
And so the amazing thing is, during any collision, whether it's like a gentle tap or a smashing impact, the total momentum of the system is always conserved.
Always.
Okay, remind me what momentum is again.
Okay, so momentum is basically a measure of an object's motion.
Okay.
So it's calculated as its mass multiplied by its velocity.
Okay.
So you can kind of think of it as the oomph factor.
The oomph.
How hard it is to stop something that's moving. So a massive truck moving fast has way more momentum than a tiny scooter, even if they're going the same speed.
Okay, so it's not just about speed.
It's about the mass.
So it's the combination.
The combination.
Of the two.
Yes.
Okay.
And this oomph factor always stays the same during a collision.
Okay, so that never changes.
That never changes.
Interesting.
However, what happens to the kinetic energy depends on the type of collision.
Ooh, okay.
Whether it's elastic or inelastic.
So there's different rules for energy.
There are.
Okay.
Depending on the type of collision.
I like that.
So in an elastic collision, like two perfectly bouncy billiard balls colliding, the total kinetic energy is conserved.
So they just bounce perfectly off each other.
Exactly.
Okay.
They bounce off each other without any energy being lost.
It's like a perfectly bouncy rubber ball.
Yes.
All that energy stays.
Stays in the system.
Okay, got it.
But in an inelastic collision, some of that kinetic energy is transformed into other forms of energy, like heat or sound.
Okay.
So think about dropping a lump of clay.
Oh, yeah.
It doesn't bounce back at all, right?
Right. It just goes splat.
Yeah, just goes splat.
And it loses its shape.
Loses its shape, and the energy is lost as it deforms.
So in an elastic collision, the energy bounces around happily between objects. And then in an inelastic collision, some of it kind of goes astray.
It goes astray, yeah.
And turns into other things.
It converts.
That's so cool.
And to make things even more interesting.
Okay, always more interesting.
Always, right.
Yeah.
We can have collisions in one dimension or two dimensions.
Like a head-on collision versus a glancing blow.
Exactly.
Right.
So one-dimensional collision is like two cars hitting head-on. They're moving along the same straight line. And in these cases, we can use the laws of physics to figure out exactly how fast each object will be moving after the collision.
So it's like a physics puzzle where you can use the before
to
predict the after.
Exactly.
Oh, I love a good puzzle.
Me too.
So like a classic example is like slowing down a neutron.
Oh, yeah.
In a nuclear reactor.
Exactly. Physicists do this by colliding the neutron with a lighter nucleus like deuterium or carbon.
Okay.
And this transfers a lot of the neutron's kinetic energy.
So they use that collision.
They use the collision
to manipulate
slow it down.
The energy.
Exactly. It's like a cosmic game of billiards.
I like that.
Yeah, right?
Yeah.
You're using these collisions to manipulate energy and motion.
Exactly.
And then we have two-dimensional collisions.
Okay.
These are a bit trickier
Okay.
to analyze.
But probably more fun, too.
Oh, way more fun.
Okay.
So these are where things can move in a plane. So think about those classic billiard ball shots.
Oh, yeah.
Where you hit one ball and it sends the other ball flying off at an angle.
Yeah.
It's like, how do they do that?
Yeah. Right.
That's some serious physics.
It is.
Wow.
To figure out what happens in these two-dimensional collisions, we have to consider the conservation of momentum in both the X and the Y directions.
Oh, wow.
So it's like...
It's a multi-dimensional physics puzzle.
It is.
My brain is starting to hurt.
In a good way, though.
Yeah, in a good way.
It's good.
I like it.
And these puzzles can reveal some really surprising things.
Okay, like what?
So did you know that when two billiard balls of equal mass collide perfectly elastically, they always move at right angles to each other after the collision?
No way. That's so cool.
It's pretty wild.
Yeah, I never would have guessed that.
It's one of the many fascinating things you can discover.
It's all fluff.
Physics is everywhere.
Physics is everywhere.
It is.
Yeah. You know, it's amazing how these, like, simple concepts can explain such a wide range of phenomena.
This deep dive has been incredible.
Yeah.
We've covered so much ground, from the, like, precise definitions of work, energy, and power to this mind-blowing concept of energy conservation.
It is pretty mind-blowing.
And the intricate dance of momentum in collisions.
And it's just the beginning.
Oh,
I know.
There's more. There's so much more. We're just scratching the surface.
Okay.
But for now, I think we need a break.
Yeah, I think we do.
Yeah.
Okay, we'll be back.
We'll be back. And we're back. Ready to dive even deeper.
My brain is still buzzing from all those mind-blowing concepts we talked about.
Yeah.
But I'm ready for more.
All right, let's do it.
Okay.
So remember how we talked about the conservation of mechanical energy and how it only applies when we're dealing with conservative forces?
Yeah, that kind of tripped me up a little bit.
What makes a force so special that it gets to be in the conservative club?
Well, conservative forces have this unique property.
Okay.
The work they do only depends on the starting and ending points of an object's movement, not the path it takes to get there.
So it's like gravity doesn't care if you take the stairs or the elevator.
Exactly.
It just cares.
It just cares about the height.
How high you end up.
Exactly.
Right.
And gravity is the perfect example of a conservative force.
Okay.
So let's say you lift a book from the floor to a shelf.
Okay.
Whether you lift it straight up or take a more roundabout path.
Yeah.
The work done by gravity is the same.
So it's just the change in height.
It just depends on the change in height.
Got it.
So with these conservative forces, we can, like, neatly account for the potential energy.
Right.
Because it's all about position.
Okay.
But what about the rule breakers?
Oh, there's always rule breakers.
There are.
In physics.
The forces that don't fit so neatly into this category, you're talking about non-conservative forces.
Okay.
And they are the rebels of the physics world.
I like them already.
All right. Friction.
Friction.
Was the classic example.
Yeah, it's always messing things up.
It is. It really is.
Okay.
The work done by friction does depend on the path taken.
So friction is that friend who always insists on taking the scenic route.
Yes.
Even when you're trying to get somewhere fast.
Exactly.
Okay.
Imagine pushing a box across a rough surface.
Yeah.
The longer the path you take, the more work friction does.
Okay.
And the more energy is lost to heat.
Friction's like an energy vampire.
It is.
It just sucks the useful energy away.
It does.
And turns it into heat.
Absolutely.
Which isn't so useful.
Not as useful, no.
I mean, I guess sometimes it is.
Sometimes.
Okay, that explains why things slow down.
Right.
And eventually come to a stop.
It all comes back to friction.
So because of this, like path dependence, we can't define a potential energy for these.
Exactly. You can't define a neat potential energy function for non-conservative forces.
It's a little messy.
It's messy.
They're energy accounting.
Yes.
Okay.
To say the least.
So it's like energy leaks out of the system.
Pretty much.
And that makes things unpredictable.
Makes things a bit unpredictable.
It reminds me of how we were talking about that car colliding with a spring. And at first, we imagined it was a perfect world.
Frictionless.
Frictionless.
Yes.
Where all the energy was conserved.
Yes.
But then we brought friction in. And things got messy.
Things got a lot more complicated.
Yeah.
Remember how the spring compressed less when friction was involved?
Yeah.
That's because some of the car's kinetic energy was transformed into heat.
Because of that friction.
Because of that friction.
Okay.
Leaving less energy to compress the spring.
So friction just throws a wrench into everything.
It really does.
It really does.
Yeah.
Okay, but even though these non-conservative forces mess things up
I do.
a little bit, I have a feeling there's still a bigger picture.
Oh, absolutely.
Of energy conservation going on.
Yeah.
We just need to,
broaden our perspective.
Broaden our perspective a little bit.
A little bit.
Yeah.
Beyond just mechanical energy.
Okay.
You're absolutely right.
Okay.
The principle of energy conservation is one of those fundamental laws of physics.
Okay.
It states that energy cannot be created or destroyed, only transformed from one form to another.
So even when energy seems to disappear, like when friction generates heat, it's not really gone.
It's not gone. It's just been converted.
It's just hiding.
It's just hiding.
It's playing hide and seek.
Exactly. Yeah. The total energy of the universe remains constant.
Whoa, that's a big thought.
It is a big thought.
Yeah.
Mind-boggling concept.
It is.
Yeah.
It really is.
It is a humbling reminder that even with all the amazing concepts we've explored, we're just scratching the surface.
Of how energy works.
Of the profound and interconnected nature of energy.
Yeah, and I bet as we continue to explore the universe, we'll uncover even more astonishing connections and mind-blowing implications.
Oh, yes, so many.
Of these basic concepts of work, energy, and power.
Absolutely.
So, dear listener,
Yeah.
I encourage you to look around with a newfound appreciation for all the ways energy is constantly being transformed and conserved all around you.
All around us.
Yeah.
Perhaps you'll start noticing the potential energy stored in everyday objects.
Oh, yeah.
The kinetic energy of moving things.
It's everywhere.
It is.
The power behind every action.
Even something as simple as walking. It's a beautiful and complex interplay of energy and motion.
This deep dive has given me a whole new perspective.
That's what we like to hear.
I'm seeing energy everywhere.
That's the beauty of physics.
Yeah.
It helps us understand the hidden mechanisms that govern the universe.
It's amazing.
And it all starts with these fundamental concepts of work, energy, and power.
But wait, before we get too carried away with the big picture.
Okay.
I remember you mentioning something about collisions, where the objects don't even touch.
You're talking about scattering?
Scattering.
Yeah. It's not magic, but it's pretty amazing.
Okay.
Unlike those billiard ball collisions you were talking about earlier,
right?
Scattering involves forces that act at a distance.
Okay, my mind is officially blown.
I know, right?
So we're talking about
magnets repelling each other, or those tiny particles physicists smash together.
Yeah, and those giant colliders.
Yeah, exactly.
Okay.
So think of a comet.
Okay.
Being deflected by the sun's gravity.
Oh, wow.
Or an alpha particle being scattered by the electric field of an atom's nucleus.
So even though they don't physically touch,
they don't touch.
There's still this exchange of energy and momentum.
Exactly.
So it's like a cosmic game of tag.
It is.
Where they influence each other.
Yes.
But they don't actually make contact.
Without making contact.
That's incredible.
It is. Yeah. And the way these particles scatter, the angles they take, the speeds they end up with, tells us a lot about the forces between them.
Okay.
It's like using collisions as a tool to probe the fundamental interactions of the universe.
So like a cosmic detective story.
It is.
We're using scattering patterns.
Exactly.
To unlock the secrets.
You'll unlock the secrets.
Of matter and forces.
Of the universe.
Okay.
So I guess it just goes to show that collisions in all their forms aren't just about objects bumping into each other.
Right.
They're about the fundamental ways
energy and momentum interact and shape the universe around us.
You've hit the nail on the head.
All right.
And it's a testament to the power of physics.
It is.
That we can use these relatively simple concepts, work, energy, power, and collisions to understand phenomena ranging from the everyday to the cosmic.
It's pretty incredible.
It is.
It really is.
Wow, we've covered so much ground in this deep dive.
I know we have.
From the precise definitions of work, energy, and power to the mind-boggling principle of energy conservation.
Yes.
and the intricate dance of momentum in collisions.
It's been a journey.
It's been quite the journey.
It has.
It truly is remarkable how these fundamental concepts underpin so much of our physical world.
Absolutely.
But I think it's time we shift gears.
Okay, I like it.
A little bit.
Right.
And explore something even more intriguing.
The concept of rotational motion.
Oh, yes.
Rotational motion.
I can't wait to see how these concepts of work, energy, and power apply to things that spin and twirl.
Well, buckle up, because things are about to get even more fascinating. So far, we've been talking about objects moving in straight lines.
Yeah, like linear motion.
Exactly, linear motion. But the universe is full of things that spin and twirl and rotate.
Oh, yeah, it's true. From planets to, like, figure skaters doing those crazy spins.
Absolutely.
Rotational motion is everywhere.
It is.
And the amazing thing is, the concepts of work, energy, and power we've been talking about, they still apply.
They do.
Just rotational motion.
They do.
Right?
But there are some interesting twists and turns along the way.
I'm ready for those twists and turns.
All right, so the first thing we need to do is introduce a new concept, angular velocity.
Linear velocity.
It's basically the rotational equivalent of linear velocity. So instead of measuring how fast something is moving in a straight line, we're measuring how fast it's spinning.
Exactly.
Okay.
Angular velocity tells us how quickly an object is rotating about an axis.
Okay.
We usually measure it in radians per second.
Radians, that sounds a little intimidating.
I know, it sounds a little intimidating, but it's not that complicated.
Okay.
A radian is just a way to measure angles.
Okay.
1 full circle is equal to 2 pi radians.
Okay.
So if an object completes 1 full rotation in 1 second, its angular velocity is 2 pi radians per second.
Okay, I think I'm starting to get it.
Okay, good.
So angular velocity is all about how fast something's spinning.
Yes.
What about the energy that's associated with this spinning motion?
That's called rotational kinetic energy.
Rotational kinetic energy.
Just like linear kinetic energy is the energy of motion in a straight line. Rotational kinetic energy is the energy of motion in a circle.
Okay, so like a spinning top has rotational kinetic energy, while a ball rolling across the floor has linear kinetic energy.
Precisely.
Yeah.
And just like linear kinetic energy depends on mass and velocity.
Yeah.
Rotational kinetic energy depends on a quantity called moment of inertia.
Okay.
And angular velocity.
Moment of inertia, that's a new one.
Moment of inertia is essentially a measure of an object's resistance to changes in its rotational motion.
Okay.
It depends not only on the object's mass, but also on how that mass is distributed relative to the axis of rotation.
So a solid sphere has a different moment of inertia than a hollow sphere, even if they have the same mass.
Exactly. The shape and mass distribution of an object greatly influence its moment of inertia.
Okay.
And therefore how much rotational kinetic energy it has.
So if I want to, like, spin something faster, I need to, like, overcome its moment of inertia.
Precisely.
To get it going.
And that's where torque comes in.
Torque, okay.
Torque is the rotational equivalent of force.
Okay.
It's what causes an object to rotate or to change its rotational speed.
So force makes things move in a straight line, while torque makes things spin.
You got it.
Okay.
Torque is all about applying a force at a distance from the axis of rotation.
Okay.
Think about loosening a nut with a wrench. You apply a force to the end of the wrench, which creates a torque that rotates the nut.
Okay.
It's all about leverage.
I'm starting to see how these, like, rotational concepts are very similar to their linear counterparts.
They are. They're beautifully analogous.
But what about power? How does that fit into this spinning world?
Rotational power is simply the rate at which work is done by a torque.
Okay.
Just like linear power is force times velocity, rotational power is torque times angular velocity.
Okay, so a powerful motor can deliver a large torque
Yes.
and spin something very quickly.
Exactly.
Yeah.
Think about the engine in a car. It delivers a significant amount of torque to the wheels, allowing the car to accelerate rapidly.
This is so fascinating. What really blows my mind is that these principles apply to objects of all sizes.
All sizes.
From tiny atoms to giant galaxies.
That's the beauty of physics. It's a universal language.
That's amazing.
That describes the behavior of matter and energy at all scales.
Wow. This deep dive has been an incredible adventure.
It has.
We've explored the fundamental concepts of work, energy, and power.
We have.
And seen how they apply to both linear and rotational motion.
Yeah, we've covered a lot of ground.
We've discovered some really mind-blowing principles like conservation of energy.
Absolutely.
And the interconnectedness of force and motion.
It's all connected.
It is.
It really is.
I'm going to look at the world in a whole new way now.
That's what we like to hear.
Every spinning object, every moving object will be a reminder of, like, the invisible forces and energy transformations
that are happening all around us.
It's amazing.
It is.
Thank you so much for taking us on this deep dive today.
It's been my pleasure.
It's been incredible. I feel like I've learned so much.
Good. That's what we like to hear.
And to all of our listeners out there, keep those minds curious and keep those questions flowing.
The universe is full of wonders waiting to be explored.
And until next time, may your deep dives be filled with fascinating discoveries.
And mind-expanding insights.
And as always, keep exploring.
Keep learning.
And keep on diving deep.